Okay, so complex numbers is, in a sense, a field of maths that expands more than what we're able to determine if we're only just working in real numbers. So we've seen a quadratic equation similar to this before, and we're asked to find real solutions to such an equation. So if we're going to solve a quadratic equation, we could perhaps use a general quadratic formula, something similar to this. And then by substituting in the numbers and simplifying, we get some kind of number where we have this here, the square root of a -8. This -8 is going to give an unreal number. So we say no real solutions. So doesn't have to just the maths doesn't have to just collapse at that point and unable to make any achievements. So this is where the role of the imaginary number comes in. So if we now think about the same quadratic equation, and we're going to solve this quadratic equation across the complex number set. So this is a set of numbers that are all real numbers, as well as imaginary numbers. So again, we get this number, and we see that this square root of the negative can be represented with an I. And that's the definition of our imaginary number. I equals the square root of -1. So having simply made that substitution, we ended up with a result, 2 plus or minus the square root of 2i. Okay, so that what we have there is what we are terming a complex number. A complex number is both the imaginary part, which is this, as well as the real part, which is this part at the front. Together it's called a complex number. And I suppose without complex numbers, without this field of imaginary numbers, we wouldn't have such technological advances, such as CPUs and complex electronic circuitry. So electrical engineering is number one developed field in the industry. That theoretical basis of it all draws on complex numbers, and without considering complex numbers, we wouldn't have such technology. Okay. Now let's look at some of the properties of complex numbers. We've got z equals x plus yi. Now there are two parts to that number. We've got a real part and an imaginary part, and we generally use this notation to represent the real part of z, which is x. It's just the number in the front, and then the imaginary part, im of z, is the y, the number that is multiplying the I. Okay, and so we use those two functions. These are what we call functions of a complex number: the real part of z and the imaginary part of z. So some things we can do with complex numbers: add and subtract and multiply, because in the end they are just numbers, and their processes are fairly straightforward and quite intuitive on how you might approach adding in an algebraic sense. So let's try this first one, z1 plus z2. If we add those two complex numbers, what are we going to achieve? So let's get the first one here, 3 plus 4i, and as the first number we're going to add 6 minus 7i. So in the approach to adding complex numbers, the real parts of the number add to give us 9, and the imaginary parts of the numbers add, where we have 4 minus 7, which is negative 3i. Okay, very straightforward. Now the next idea. Okay, now let's have the next part. Now this is a situation where, where we have a subtraction, but we've also got this factor of 2 there on the Z2 complex number. Now this is what we call scalar multiplication, and this is so far a multiplication that is not multiplying complex number by complex number, but by some constant like number 2. Scalar multiplication. So how are we going to approach this one? Now it's very, again, straightforward as before. We can have, using our 2 complex numbers, 3 plus 4i minus, and now we've got a factor of 2 that we have to consider, 6 minus 7i. And in simplifying this, there's the real parts, 2 times 6 is 12, and the complex, the imaginary parts, 4. Now the negative 2 multiplied by negative 7 is positive 14 as the imaginary parts of the number I. And in simple, we have negative 9 plus 18i. Okay, so those scalar multiplication again is quite straightforward. Okay, now the last thing to consider is what happens if we have an expression 2z2 plus 3z1, but we're interested in the real part of it. This is what this real function of that complex number operations is after, just the real part once we've simplified it. So let's carry out a calculation first. Let's simplify what we have. We've got 2 of 6 minus 7i plus 3 of z1, 3 plus 4i. Okay, so that gives you 12 minus 14i plus 9 plus 12i. Now here we need to determine the real parts, so that gives us 12 and 9 is 21, and the imaginary parts is negative 2i. Okay, and from that we're after just the real part of that number. Okay, so the real part of 21 minus 2i is the number 21, the first part. Okay. Okay, so far we've looked at some basic operations. Before we continue, at any point in this video, if you wish to review the workings out, you can always, go back to a previous scene. Remember to press pause, have a talk about it, or write some things down in your notes, and then you can continue on with the video. Okay. So, what's the next important idea we're going to look at? When we have a situation where we have complex numbers on either side of an equal sign, where we're interested in being able to equate two complex numbers and identifying what are unknown elements. So in this we have, let's determine the values for x and y for on the left hand side, and we have some expression on the right hand side. Okay, let's see if we can do the workings. So we have 4 minus 3i. Now in the second bracket, let's multiply it by -2, and we get positive 8i. And simply we can see in collecting the imaginary numbers, we'll have 4 plus 5i. Now comparing that right hand side with the left hand side, we can therefore conclude that x has to equal to 4 and y has to equal to 5. So that's one simple example of showing this type of problem. Okay, so now let's look at multiplication of complex numbers. We've got two complex numbers, z1 and z2. Let's first take z1 and multiply by I. Okay, a factor of I. And we can see from there, quite simply, again, the same approach, I multiplied by 3 plus 4i, and treat it like an algebraic number, expand the brackets, multiply both terms, 3i plus 4i multiplied by I, which is I squared. Okay, now from that, how does this simplify? Well, first off, we need to remember what is I. I is the square root of -1. So I squared is squaring that square root, which is your inverse operations. So that will have a value of -1. So let's put that in there. 3i minus 4 now. And we have a situation where the first term has now become the imaginary part, and the second term has become the real part. And there's been a change in sign as well. And shortly we're going to examine what are the implications of that geometrically. And we'll introduce the idea of the Argand diagram. Now the next type of complex number multiplication is where we've got these two z1 and z2 complex numbers, and we're going to multiply them two together. And let's see how that turns out. So first off, let's put down the first complex number, and because it's been operated on with another complex number, we're going to retain it in brackets like we have here. So as you can see, in this multiplication, it's just like a double bracket expansion, okay, which we've practiced numerous times. So the first term we'll get 3 times 6 is 18, minus 21i, plus 4i multiplied by 6 is 24i, and then finally we've got negative 28i squared. Now from that we can collect our like terms, so the imaginary parts of the numbers can add. Okay, so we will have positive 3i, and then this number here is an interesting one. This I squared, we know, we can see from above, it is equal to -1. So it then, this imaginary part becomes real. So we'll have a positive 28 as a term in that workings out. and now that's going to combine with the real part, the 18. So we're going to get a 46 plus 3i as our final answer. Okay, so with this complex multiplication, there's a general pattern or form that every double bracket in this case will take. So in general, if we take two complex numbers, a plus bi multiplied by c plus d, then there will always be a final general form in the expansion. And what occurs is with this I multiplied by I, this I squared term that we saw equaling -1, it will give us an important thing to remember to do. So in this situation, we'll have an a multiplied by c plus an ADI plus a BCI, and then finally with the last two, the BI multiplied by DI, that I squared will give you a -1 with the BD multiplying. So that last term is in fact real. So we're going to write it up top. So we have an AC minus BD as a real number. And then the imaginary part, AD plus BC. Okay. Okay, so that's just a few examples of multiplication. The next important operation we're going to look at is division and see what will happen about that operation. But before we get on to division, I'm going to introduce you to the idea of the Argand diagram. And this is your graphical representation of your complex numbers, and it behaves identical to that of a Cartesian plane. It's just like plotting an x and a y coordinate. So if we have two complex numbers, then let's see how such numbers can be plotted. And then we've got a third complex number. This is the sum of the two, z1 plus z2. We will also plot that and just get an idea on how that would be represented geometrically. So in plotting out these numbers, very simple. The horizontal axis, which is your x-axis in your Cartesian plane, that's going to take all the real numbers, and your imaginary numbers we're going to put in the vertical axis. Let's have a look. So let's plot z1. Let's say 1. About there is a real number 3, and maybe up here is the to scale about 4. So your z1 is a point here, 3 plus 4i. Okay, now that could also be written as an arm from the origin. Okay. Now, one thing you may remember from last year when looking at vectors, when plotting vectors, behaves very similar to the way we're drawing complex numbers on an Argand diagram. So we actually treat complex numbers as a vector in some sense. Let's continue. So now let's look at z2, where we've got 6 minus 7i. So 6 as a real number is probably down there, and minus 7 will be much lower as far as down that. So we will have our z2 6 minus 7i is a complex number, and again some point away from the origin there. Okay, now when we have an Argand diagram and we want to be able to plot our two complex numbers together, z1 plus z2. So first let's just get an idea of what that is as a number. Okay, so we've got 3 plus 4i z1 and we're adding z2. So we have 9 as the real part and negative 3 as the imaginary part. Okay, now that number is a lot higher out of our domain at the moment, so nine on the real axis will be as far out as about here, and the negative 3, 1 to 3 can be maybe down here. So we can see we have a point as far as over here as being our z1 plus z2 number. So that's one way of plotting that in Argand diagram. You can work out the number, do the addition, and then plot the real part, imaginary part on your Argand diagram. Alternatively, could we approach that in another way, thinking about the vector sum of z1 and z2 as we see it? So let's actually start from z1. This is what we had drawn for z1. Okay, now if we take z2 and just keep the same size, keep the same angle in it, but just reposition it in a different point on our Argand diagram, in the same way in which a vector identifies the size and direction, but doesn't really matter on where it will begin. So if I draw another vector type line from z1 that mimics z2, such that it is same length and same angle from the real axis of z, then we can treat it as this z1 plus z2 here as some path in order to get to the result. So we've travelled from z1 and we've added onto our journey z2 to get to our sum, which is this sum of our complex numbers, 9 minus 3i. Okay, so we can see geometrically that the sum of complex numbers is almost like a path, creating a path from the origin to the final point. Okay, so from here let's have a look to see what perhaps multiplication how that can be represented on our Argand diagrams. So let's take two complex numbers and let's see if we can represent a few of these different products. Alright, so here we have the first one, 2 lots of 2 multiplied by z1. Now remember, that's what we call scalar multiplication, and it's just some whole number 2 multiplied by the complex number, so we get 4 minus 2i. So let's plot both what we have there. We'll plot z1 and then we'll plot 2z1 and let's compare the difference. So z1 might be about there. So 2 minus I. Then 2z1 is another number that's down here. And what's the difference between the two? Well, if we drawn accurately, we might be able to see that z1 is that long, and 2z1 is another line in the same direction precisely, but we have twice the length, and essentially this is what we've achieved. Geometrically, scalar multiplication is just doubling the length or tripling the length depending on the factor. It's increasing the length by a certain factor. Okay, then what about when we multiply by a factor of I? Is that going to increase the length of the complex number on Argand diagram, or do you think we'll do something different? So let's work it out. As a number, we might get something along the lines of I minus multiplied by 2 minus I gives us 2I plus 1. Okay, remember I squared is -1, so that's where the negative became a positive. So let's first, we've got z1 in the green. Now let's plot IZ1. 2. Okay, there it is. So this line here is IZ1 as the complex number on the Argand diagram. Now what's the relation between the two there? This one and this one, the green one and the new red line that I drawn. Well, if we look closely, they are 90 degrees to each other. And this is the role of multiplying by I, is we have rotated our complex number by 90 degrees. Now, before we get too excited, let's see if that's going to work on Z2, a different complex number. So first let's plot Z2. So Z2 is 3 plus 2I. 1, 2, 3 plus 2I. It's about there. So that is Z2. Now, IZ2, I multiplied by Z2 gives us I multiplied by 3 plus 2I is now -2 plus 3I. Let's put that on our Argand diagram and let's compare. So -2 plus 3I. Going to be about there. IZ2. Alright, now I'm going to draw those two lines in. First here is our different color, maybe blue. Here is Z2. Now here is IZ2. And what's the relationship between those two lines, the purple line and the blue line? And again, we will have them at 90 degrees to each other, right angles. And in fact, the role of multiplying by I is a rotation by 90 degrees in the anti-clockwise direction. Can we see we've gone this way, and in the first one we've gone that way. So 90 degree in an anti-clockwise direction. Okay, so I wonder what then would be the role of multiplying by I squared, or more precisely, multiplying by -1 by a complex number. You might assume, yes, it rotates the number on the Argand diagram in some way, but by how much? How many degrees do you think the rotation will occur? Okay, the next thing we're going to look at is what's called the complex conjugate. Now, with this complex conjugate, it's important to first highlight the role of this thing. It's called the modulus of the complex number. Now, the modulus, as we know, it's about finding the size of a number, not so much the direction. So we can think of it as the distance of the number from the origin. So if you find the modulus, it's if we think about an Argand diagram, so at some point over here, then we're after a distance from that point to the origin, such as this. There's some point, then we're thinking about what the modulus of z would be, or what's the length of that line. Okay, now the modulus here is worked out by, of a complex number, is worked out by this relationship, x squared plus y squared. So we square the real part, square the imaginary part, and then square root. This is in fact precisely identical to Pythagoras' theorem. Pythagoras' theorem is finding out the lengths of a right angle triangle, so you can interpret on an Argand diagram. We have two parts to our complex number. We've got your vertical and your horizontal part, the real and the imaginary part of our complex number, and we produce a right angle triangle problem where the hypotenuse can be worked out using Pythagoras' theorem. Alright, so how are we going to, why is this important? It's important for division and how it connects to what we call the complex conjugate. Okay, so let's define what the conjugate is. So for any complex number, z equals x plus yi, then the conjugate is where we put a negative in front of the I, or a sign change. So if the number was positive originally, then we will have a negative for the sign change. And we read the conjugate as z bar. So some properties of a complex conjugate, let's examine them. We've got two situations here. One is z plus z bar, and the other one is multiplication. So what will happen? Let's take the general sense of any complex number, x plus yi, that's z. Now let's add its conjugate, x minus yi. Now, as we can see, we have two x's there, and the y's will cancel out through subtraction. So we started with a complex number, and we added its conjugate, and we ended up with just a real part, a real number only. Let's see what will happen for multiplication. So take complex number, x plus yi, and let's now multiply by its conjugate. And when we expand this out, we will have first, instead of expanding each term out one by one, what kind of double bracket do we recognize here, and what would be the equivalent expansion rule? And you might notice that this is the same as the difference of two squares expansion. So that's equivalent to the first term squared minus the second term squared. Second term is yi. And in squaring I, we get -1. So the subtraction here becomes positive. X squared plus y squared. Now this here looks something familiar, because if I relate that to the modulus, here is my x squared plus y squared. And that's what we've obtained down here. So another way we can represent this number is modulus of z squared. And there's a special identity relationship that we found there. Is complex number multiplied by its conjugate is its modulus squared. Okay, so working with the complex conjugate is important for division. So if we have division of complex numbers like this, z1 divides z2, or simply it could be written in a fraction form, then what kind of result we'd want from that is an answer that is just like a complex number, x plus yi. That's what we want to obtain. Now, in order to do that division, we're going to have to use the conjugate. And let's see how. We're going to do it in a process of rationalizing the denominator, just like you would with surds. If you have the square root of a number in the denominator, we have to go through a process of rationalizing that denominator to get the square root up top in the numerator. Same thing with complex numbers. So what we're doing here, we look at the denominator z2, we have to multiply by a fraction, special fraction that has the value of 1. Same thing on the numerator and denominator. So we multiply by its complex conjugate in the denominators, because, as we saw, multiplying by a complex conjugate returns a real number. And so it's no longer the imaginary part. There's no imaginary part left. And we also saw that complex number multiplied by its conjugate gives the modulus squared, in fact. So it must be squared. Okay. So let's try that as an example. Here is 3 plus 2i on 1 minus 2i. So let's work through this little problem. We're going to multiply by its conjugate as a fraction. So 3 plus 2i in the numerator, divide 1 minus 2i. So now multiply by its conjugate, 1 plus 2i, and the conjugate onto itself, 1 plus 2i in the numerator. So from that we have a double bracket type problem in the numerator there. 3 plus 2i multiplied by 1 plus 2i, and the denominator, again, it's a double bracket type expansion, but if we notice, it's the same type of number but opposite signs. So it's like the difference of two squares, and we saw that simplifies down to the modulus squared, which is simply the x squared plus y squared, the real part squared, and we add the imaginary part squared. So the real part squared is 1, 1 squared is 1, and we're going to add the imaginary part, which is 2. 2 squared gives us 4. Okay, so now let's simplify our numerator. We have 3 plus 6i plus 2i minus 4 all over 1 plus 4 is 5. Now let's collect our like terms, bringing the real parts and the imaginary parts together. We have -1 plus 8i over 5. Now that could be left as so, but we might want to represent that as two fractions. So we've got negative a fifth plus 8/5 I. Okay, so finally we're just going to look at a couple of problems from the coursework. This one is from exercise 4a. Alright, solve the following equations for values of x and y. Now, here we've got two complex numbers and they've been equated to each other, the left side of the equal sign and the right side. So from that, we're going to simplify what we see. So we might have in the first, let's identify that the 2x plus 3, that's the real part on the left hand side, plus 8i is equal to this is the negative 1, that's the real part, and 2 minus 3y, that's the imaginary part. So if we equate the imaginary parts together, this bit and this bit, equate them together and re-equate the real parts together, we'll end up with two little equations. So the first equation is, let's equate the real parts. 2x plus 3 on the left hand side, well, on the right hand side that's the same as negative 1, and that presents us with one equation. The second equation is now equating the imaginary parts. 2 minus 3y on the right hand side, now we're told that's the same as 8i. Now to work out what x and y is, we've got two linear equations that we are going to solve. So from the first equation, our 2x is equal to negative 4, x is equal to negative 2. And the second equation, we've got negative 3y is equal to 6, and y will equal to negative 2. And we've got determined our values for x and y. Okay, our final problem, we're going to do a multiplication and a division of complex numbers. So z is 2 minus I. Let's see if we have to simplify the two expressions. So part A, we've got z times z plus 1. Now z is 2i, so let's substitute that in. That's z multiplied by z plus 1. So again, write down z plus 1. Okay. So 2 minus I, and we can see the second bracket simplifies to 3 minus I. And now we have a double bracket expansion. So off we go. 2 3s are 6, minus 2i minus 3i. Now negative I multiplied by negative I. I know I squared is negative 1, and negative times negative is positive, so we're going to have overall a negative 1 there. So finally 5 minus 5i as our final result for part A. And B, let's check to see how that works. Z minus 1 over z plus 1. Okay, so first step, let's substitute in our complex number z. In the numerator, 2 minus I subtract 1, and the denominator, 2 minus I plus 1, gives us 1 minus I over 3 minus I. Now, in performing this division, we have to look at the denominator and multiply by its complex conjugate onto itself. So let's do that. Multiply by a fraction where 3 plus I. 3 plus I, that's its complex conjugate. Now, the denominator is simple because that becomes x squared plus y squared, which is the modular squared. And we use that little shortcut rule to calculate the denominator. So 3 is your x value, 3 squared is 9, and y value in that will be 1 because the coefficient of I is 1, plus 1. And our numerator we have treated as double brackets. So 1 times 3 is 3, plus I minus 3I, and we have now I squared, which is negative 1, and that negative 1 multiplies another negative, so it becomes positive 1. Finally, we have 4 minus 2I all over 10. Fortunately, we've got all common factors there of 2. So this time I'm not going to run into that Dulcere desktop trial. 2 over 5 minus 1 over 5I as our final result. Okay, so that's the extent of what we're covering for this session on complex numbers, and I'd like to leave the rest up to you. Thank you very much.